Okay, stability. Before that, we need to review some of the basics. I know you already know this, but still need to review. The Bode plot. For example, if I have a transfer function like this, right? So how many poles do I have? Two poles, right? What the poles are? What are the poles? P1, P2, right? Not because I wrote it in this way, it's because you set it to 0. You find that when S equal to P1 or S equal to P2, it gives you 0, right? Okay, so how do you draw it in the Bode plot? Then we need to remind ourselves again, this is the log frequency. And what is the y-axis? 20 log the magnitude. Okay, not the magnitude. I'm only showing the magnitude, right? And how do you do it? We assume that it's flat at the beginning. Then what will happen? Negative 20, thank you, the decade, when you see the first pole. And then you continue another 20 dB. And the point is that it keeps adding, it accumulates if you have a new pole, right? Say again?
You could also annotate the original starting gates.
Oh, okay. So he is trying to be straight. He is saying that what I'm drawing is not really for this whole function.
It's works fine for generic,
yeah,
as a generic function.
Good.
You can just move the 0 up.
All I try to do, yeah, thank you. Yeah, it's very picky. Thank you. That's right. Yeah, but the purpose here is just review that it goes down by 20. Okay, good point. Now, then let's look at another function, which is this. How many poles does it have? No pole. How many zeros? 2, okay. 0, do I need to add ES? No, right? Just S.
Way easier to understand than the 132 lecture.
Okay, so how do you draw the Bode plot for magnitude? Again, this is log frequency, 20 log the magnitude, right? So this time I will start from 0, so you don't get me trouble.
Yeah, we start somewhere flat. But we have one at C1.
C1,
again.
C2, right? So this plus 20 plus 20 plus 20 equal to plus 40 dB per decade. Okay. The main point here I want you to, for this slide, is that emphasize that they accumulate, they keep going. Okay. And we proved that before. Okay. But now we are talking about oscillation. We need to look at the phase also. Okay. So what is the phase? Because all the gain, you say H, right? It's a complex number. You can say it's equal to alpha plus J beta, for example. J is square root 1. We can also, you know that you put in the complex plane. I can also say that this is equal to magnitude of A times e to the power I theta, for example. Yeah. For example, this is real. This is imaginary. You have a point here, right? This is alpha. This is beta, right? And then, of course, you can say, okay, how about I say this is H, magnitude, right? And this is theta. I just remind you about this. So what we plot in the last slide is how this magnitude change with the frequency due to the frequency response. But to completely describe this H, of course, you can use alpha, beta, but it's not that useful for electrical engineering. Using phase diagram would be better, right? So we want to describe the theta also. That's why we have the phase. So if you have a pole, for example, I think we only need to draw one pole, yeah. What will happen? We won't go through the derivation, and of course you learned that before. We just review. Log omega again, but this time is the angle of h, which is theta, instead of the magnitude of h, right? So at the beginning, we assume we have 0 change, we start with 0. Let's say like the equation we have here, right? When you have 0 frequency, the gain is 1, right? 1 is a real number. What is the phase of a real number? What's the phase of a real number? 0. Because it's all on this real axis, right? So the theta equal to 0. If it's purely imaginary, it's all on this, right? Then it will be 90 or negative 90, depends. Anyway. So I say the wrong thing. For real, if it's positive, then it's 0. For negative, it's 180, right? We need to be clear. Okay. Now, when I first meet my pole, this is my pole P1. How do we draw it? We only know this. We say if I'm at 0.1 of P1, for example, if my pole is 1 gigahertz, when I reach 100 megahertz, it will start decreasing. Okay? It will start, and then when it reach 10 times of P1, 10 gigahertz, then it will saturate. How does it saturate? It will have a shape like this. And this is negative 45 degree. And this is negative 90 degree. Okay? Just take it for granted. You can prove it. And I think it was proved in other previous classes already. But the most important thing is to know that at pole P1, it reached negative 45 degree. And it will stop when you reach 10 times of the pole, stop at negative 90 degree. And it will start changing when it is 1/10 of the pole value. Okay, unlike the magnitude plot, it only start changing in our plot, right? In this approximation, the Bode Plot rule, it only change at P1. And then it change forever, keep reducing. This is the main difference. This one start earlier, 1 decade. This is called 1 decade, 10 times less. And it will stop changing after 1 decade higher. Stop changing, right? It's not keep going down. It won't be negative 135, 180, or keep going down. It just stop at negative 90. This is very important for our analysis later, okay? So similarly, it's easy to memorize. If you have a 0, what will happen to it? Can you guess, actually? Let's say I have a 0 here. What will happen to the phase, the angle of this transfer function? It will go up, starting where? Thank you. Yeah. It's just the same. 0.1 C, then you go up. And then when do you think it will go up forever? 10 Z. When you reach 10 times of the 0, it stops. And can you guess what the value will be? 45 and 90. Right? So it's easy to memorize if you memorize one of these, right? So done. That's it for this page, right? So remember this. Let's look at this. This is the magnitude plot, okay? Can you, maybe I give you 1 minute, try to plot the angle. How does the angle of this H change as a function of the frequency, right? So please start thinking about that. I will just draw the coordinates for now. And I assume that they separate very far, okay? So maybe W omega Z is 100 times of omega P.
132 way of drawing phase plot. It's just vertical lines.
Okay.
But it's difficult to do one side and then do the curve. So if you set the scale to it, technically a vertical line is curved.
Oh, say again.
There's just an easy way to do it. You can literally just bring those dot lines down, draw a square at, when it's going down, it's gonna square down. When it's going up, it's gonna square up. And then hit each one of those angles and then draw the curve around. Yeah, you find the center point of each one, depending on the amount of angle shifts. Because it could be a S square, for instance.
No, you are telling me how to draw this easily, or you're giving me the answer?
Either way.
We're discussing how to best draw
I'm
it.
saying there's instead of doing decade before, decade after, like that, you can just draw a square wave and follow.
Oh, yeah. So
Oh,
since
okay,
we're
okay.
saying the scale is still high, we could skip doing the 45-degree angle and just say that due to the high scale, it can be visualized as a square wave.
I see. Okay. I thought that you're trying to teach me how I can draw this dotted line in straight line. There's some tools that I can do it.
Well, there absolutely is. It's you need to convert all of your presentations to a different format and finite.
Okay, so let's start. So I already draw the dotted line for omega p1, omega c, omega p2, right? So I know that 1/10 of them are important. So I try to 1/10 and 10x are important, right? So I will start from here. I know this is a pole, so what will happen? You will go through and then stop at 10x and then flat out, right? And this is how many? Negative 90, right? So let me label this. This is 0.1 omega p1, and this is 10x of omega p1. And then I see the z. What will happen?
We're going to go back up.
Go back up. Because the effect of the pole stop already. You just keep at 90, right? So you go up. Again, go up by how much?
By 90 degrees.
By 90 degrees when you reach 10x of z, right? This is 10x of omega z. Okay? And then what will happen again? Back down again, another 90. What is the total phase shift? We call it phase shift. At very, very high temperature, very high frequency. Huh? Minus 90. Yeah?
I mean, high temperature and high frequency
But
related.
what is the change of the magnitude at very high frequency? You would zero. Yeah, you'll be keep going down. But this one is always negative 90. So this is something we will play with, okay? Now, again, I'm repeating. Not really repeating, it's useful. Then let's construct the Bode plot of one pole, two pole, three pole system. But this time we care about the magnitude and also the phase, okay? So the first, I will be quick. This is the magnitude. I'm not going to write 20 log dB. And I know that it will go here and then go down by negative 20 dB per decade, right? And then this is the phase angle of H. And I know that it will keep going and then it will go down and then give me negative 90 forever. Okay, agree with this? Any questions? Now, what you have two poles? Again, you will hit the first pole, negative 20, hit the second pole, negative 40. Right? What happened to the angle? Great.
Yeah.
Negative 90, right? For the first pole. And then when I see the second pole, it will go down again. negative 180, right? This is negative 90 degree. Okay? So you see that for one pole, you always at negative 90 degree. You won't have any oscillation, no matter how you hook up the circuit. But at two pole, it's kind of marginal. You will get negative 180, but theoretically, you only get 180 when you reach infinity. This is just a Bode Plot rule. We say at 10x, I reach negative 180. But in reality, the function is smooth. It's just very close to negative 180, right? Again, in principle, you won't oscillate if it is very clean, okay? So in order to get oscillation, we try this. I have three pole. First pole, second pole, third pole, negative 20, negative 40, negative 60, right? Very steep. And what will happen to the angle? You will first reach negative 90 when you hit the first pole, then negative 180 when you hit the second pole, then negative 270 when you hit the third pole. This is negative 180. No. What I'm talking, yeah. And this is negative 90, right? The main point is, within finite frequency, I already reached negative 180 for free pole. Okay. Any questions? If no, then now look at the oscillation condition. Is this familiar to you? What is this? Closed loop gain, exactly, right? We have been using A, but we say A is a transfer function, right? So let's look at this circuit. It has a feed forward, which is H of S, and it has a feedback. We assume K is larger than 0 because you see many examples already. For example, the K here is just a resistor. The K here is just a resistor divider. It's well controlled, usually passive, have a very good frequency response, right? The problem will come from the transistor because you have learned the high frequency response, CGS, CGD, CDB, CSBD, right? All these things that can introduce the pole at very high frequency, right? Remember, when we do the high frequency, we find the pole 1, pole 2, input pole, output pole. These are due to the parasitic capacitor, right, at high frequency. So here we assume K is purely real, and maybe let's also assume this is positive. I forgot to write this, right, just for the sake of discussion. It can be negative, then you just hook up the comparator in another way. Now, at low frequency, we know that KH must be positive, right, at low frequency, or negative. That doesn't matter. If it's negative feedback, they must be positive, right? So at low frequency, this is a very nice negative feedback. But however, just look at this equation. H is going to change when the frequency changes. There's a possibility KH equals to -1. Do you agree that we can have this possibility? Because this depends on frequency. When KH equal to -1, this becomes 0. Blow up. It basically is saying that even you have very tiny input, 0 input, I have a very large output. And it basically is saying that at that frequency, even if it is just noise from the cosmic radiation or some very tiny noise come from the Tesla driving through the street, right? Very tiny. It's going to amplify and then mess up your circuit. And that will cause the oscillation. When KH equal to 1, what does it mean? It means its magnitude equal to 1. I mean, KH equal to -1, it means magnitude equal to 1, and the phase angle equal to -180. Is that okay? That's it. How do we see it? For example, I have a sine wave coming in. This is plus, so good. Then I will also get a plus here. Yeah. Then I go through this amplification. But unfortunately, this one becomes negative at high frequency, at that particular frequency. Originally, it would just go through as it is, right? I mean, amplify. But now you get a phase shift by 180 degrees. When the input is high, the output is low. When the input is low, the output is high. Then you go through K. But K is real and positive, right? Passive, just a resistor. So you will get the same thing. But now you're going to do subtraction. Originally, if you don't have this phase shift, you do subtraction, fine. High minus high, then I have smaller signal going in, right? But now you are subtracting a negative number. It means you are adding them together. This is 1, this is -1. 1 minus -1 becomes 2. So you have a larger amplitude when you go to here. You are not doing negative feedback anymore. You're doing a positive feedback. You set up the circuit as negative feedback. But because this one has a phase change, originally you want to subtract a positive number, it becomes subtracting a negative number. Then this get higher. When this get higher, you add more, keep looping, eventually the whole circuit blow up. I mean, not explosion, I mean the signal will just go to rail and rail, right? Then you don't have any amplification anymore. That is the idea of oscillation. Okay? This one is like saying that h of s divided 1 minus 1, right? Then you blow up to infinity. Okay? Any questions? Good. So how do we avoid this? In order to avoid this, first we need to understand two concepts, is so-called gain crossover frequency. And this is by looking at this feedback factor. I mean this or loop gain, right? When we try to see when it reach 1, okay? For example, in this case, this is not the Bode plot of the whole circuit, it's only the Bode plot of this KH. This is the gain crossover frequency, because it is the frequency at which the gain become 1, 20 log 1 is 0, right? It means it's low enough. Why we care about this? Because think about this. Even though you have positive feedback, if your gain is smaller than 1, you won't keep accumulating to infinity. Okay? Of course, there's more complicated stability theory behind, but you just think it this way. Okay? So, if I can avoid this phase shift before the gain, if this phase shift only occurs after the gain is less than 1, then I won't have the oscillation, right? So here is saying that when the gain is reaching the gain crossover frequency, right? No, I mean this point is the gain crossover frequency. Sorry, I'm messing you up. So are you okay with this? Gain crossing over frequency is at which you have gain equal to 1. Unity gain, yes, unity gain, very good, which means 0 dB. And then there is another frequency we care about called phase crossover. It means when your phase becomes negative 180. Because when it is negative 180, it becomes negative, right? Here. Yeah? It's going to give you trouble, right? So in this case, this part is the phase crossing over frequency. Because at this point, your phase becomes negative 180. Okay, now look at this. I have the phase crossing over frequency smaller than the gain crossing over frequency. Correct? The phase crossing over frequency is here. Gain crossing over frequency is here. It means I reach negative 180 earlier than it diminished to 1. So it means when I'm at negative 180, the gain is still larger than 1. So I will run into the oscillation problem, right? So this one will oscillate. Or on the other hand, instead of saying oscillation, we say it's not stable. Okay, let's look at another situation. This is the gain crossover frequency. And this is the phase crossover frequency. It means that when I reach negative 180, my gain is smaller than 1 already, right? Because 0 dB. It's just that you don't have much amplification, although now you have this positive feedback, there will be no problem. And in this case, we say the gain crossing over frequency is, maybe I make it the same as the other one. I say the phase crossing over frequency is larger than the gain crossing over frequency. It means that you already drop the gain to be less, I mean, not the gain, but should be the KH, right? The loop gain. Drop it to be less than 1 before I reach negative 180, before I'm going to have true positive feedback. Then this is stable. It is, I mean, you take this for granted, right? We did not prove it. We just hand-wavingly say that, but I hope you understand we have two concepts, gain crossing over and phase crossing over. Right? And they're defined by the magnitude and the angle. Right? Okay, any questions? Oh, you learned this before in other class, right?
But this explanation is a lot more understandable.
Okay, great. Yeah, because it's the second time. Okay, so now, because we don't go too deep, we don't really do too much. Okay, so what is phase margin, right? You already know, right? So phase margin is that now you understand in order to be stable, my gain crossing over frequency need to be smaller than the phase crossing over, right? It means I want my gain to be on the left of the phase crossover. And you can imagine as an engineer, nothing is abrupt. Everything is continuous. Do not think that as long as I have it, the gain crossing over less than the phase crossing over, I will have a perfect solution. There must be some problem, right? You want to have a large enough margin to have a good stuff, right? So just like here, when the gain crossing over is equal to the phase crossing over, then you don't have margin. You will oscillate, okay? But what you say, let me move it a little bit smaller so that it is less than the phase crossing over frequency. Yes, theoretically, it does not oscillate forever. But if you apply a step pulse to it, it still oscillates. This is called ringing. Ringing is a big problem, particularly for power electronics, because this ringing means that you are bringing the voltage to be higher than VDD. You are going to break your device. You need a device that can sustain maybe 2x of what it's supposed to work at. So ringing is not good. Of course, another problem is that when you're ringing, this signal are wrong. You cannot take them. Then it means take longer time to process the signal. Your whole system is slower actually. Okay? So you want to have enough distance between them so that when I have step wave function, it will go up rather smoothly without ringing. And of course, again, this part is the time you need to wait, unfortunately, right? So what is the phase margin? Is phase margin basically is saying that what is the angle of between 180 minus 180 and the angle corresponds to the gains crossing over. Because for when you have this gain crossing over, right? Okay, let me just finish it. When you have this gain crossing over, you will get the angle. This is the angle when you are at the gain crossing over frequency, right? And then the difference between them is the phase margin. And usually you want to have like 45 degree or 60 degree phase margin. Okay, so let's stop here. I still have 2 more slides, but we will do it on Monday.